You're sitting on the sofa right now with snacks in your hand, eyes locked on the screen. You look around the room and then back at yourself, and the same question surfaces again. How do these people actually protect everything when the systems around them start to break down? You follow the rules. You work hard every single day, yet they seem to have options that remain out of reach for almost everyone else. A part of you already suspects they operate with layers of protection most people never see. You are not being unrealistic for asking how they do it. The usual assumption is that a private jet solves the problem of escape. But what happens when speed alone is no longer enough? When governments can freeze assets across borders? When financial systems become unreliable? Or when large-scale disruption makes normal movement dangerous? A jet by itself does not guarantee safety. The real protection at the highest level of wealth is no longer found only in the air. It is built deep underground, in facilities designed for long-term autonomy. Over the next 20 minutes, I will explain exactly how the 1% designs, builds, and maintains these mega bunkers. We will examine the engineering that makes extended underground living viable, the security systems that make physical access extremely difficult, the legal structures that protect ownership, and the ongoing costs they accept as the price of having a genuine last option. If you want to understand how serious wealth is actually defended when conventional systems can be taken away or shut down, stay with me until the end. The question at the conclusion may change how you think about your own security and resources going forward. Most people still picture a bunker as a basic reinforced room with supplies stacked inside. At this level of wealth, that image is considered almost primitive. These are not small shelters. They are fully engineered underground facilities built at a scale that can support multiple families and essential staff for years without external help. The physical footprint is often larger than many luxury homes on the surface. Inside, you find properly finished living quarters, professional kitchens, entertainment areas, medical facilities, and agricultural systems capable of producing food indefinitely. The goal is not short-term survival. The design goal is to maintain operational continuity and a high standard of living while the surface world becomes unstable or inaccessible. This difference in ambition is what separates ordinary emergency planning from the approach taken by those who treat resilience as a core part of wealth management. Keeping people healthy and functional underground for extended periods requires systems far more sophisticated than basic stockpiling. Air is continuously processed through multiple stages of filtration. The first stage uses high-efficiency particulate air filters, rated at 99.97% removal for particles down to 0.3 microns. This captures dust, bacteria, and most biological agents. The second stage employs activated carbon beds with impregnated media to absorb chemical vapors, volatile organic compounds, and certain toxic gases. In advanced installations, a third stage adds molecular sieve materials or specialized chemical scrubbers to handle specific threats, such as carbon monoxide or acid gases. Ultraviolet germicidal irradiation follows to inactivate any remaining microorganisms that pass the physical filters. Positive internal pressure is maintained at all times, usually between 5 and 15 pascals above ambient, to prevent unfiltered air from leaking inward through any small breach. Carbon dioxide levels are actively managed through chemical absorption beds using soda lime or similar compounds, while oxygen is replenished either through pressure swing adsorption generators or in some military-derived systems through electrolysis of stored water. Humidity is tightly controlled between 40 and 50% using desiccant wheels or chilled water coils to avoid both mold growth and respiratory discomfort during long stays. The entire air handling system is designed with redundancy, multiple parallel trains, so that maintenance or failure of one unit does not compromise the environment. Water management follows an equally rigorous multi-barrier approach. Raw water from wells, stored tanks, or condensate collection first passes through sediment filters, to remove larger particulates. It then moves through activated carbon to reduce organic contaminants and improve taste. Reverse osmosis membranes provide the primary purification step, rejecting dissolved salts, heavy metals, and most microorganisms at rates above 95%. The permeate is then polished with ultraviolet disinfection at 254 nanometers to achieve greater than 6 log reduction of bacteria and viruses. In higher specification facilities, an additional stage of ozonation or advanced oxidation may be included for residual pathogen control and taste improvement. Gray water and black water are collected separately, treated through biological reactors or membrane bioreactors, and then passed back through the same purification train until they meet potable standards again. Large buffer tanks store treated water for immediate use, while raw storage provides years of reserve in case of complete system isolation. All critical pumps, valves, and sensors are installed in redundant pairs with automatic failover, and the entire plant is monitored continuously through a building management system that logs water quality parameters in real time. Power architecture uses layered generation and storage, including backup generators with substantial fuel reserves, and in more advanced installations, geothermal or buried renewable sources. Food production relies on controlled environment vertical farming that can operate continuously with minimal external inputs, backed by preserved stocks and supplementary protein systems. Lighting employs full-spectrum LED arrays calibrated to replicate natural day-night cycles, protecting both physical health and psychological stability over long periods. The cumulative effect is that occupants can remain subterranean for many months with limited physiological or cognitive decline upon reemergence. This represents environmental and biological engineering executed at the highest level rather than crude survival preparation. Individuals at this wealth tier decline to accept health trade-offs as the price of security. They instead engineer away the biological costs of extended underground residence through precise system design. Physical fortification alone is not considered sufficient protection. Entry points are protected by massive blast-resistant doors built to specifications similar to hardened military infrastructure. These doors likely weigh between 20 and 50 tons each. Depending on the threat level, the facility is designed to withstand. They are constructed from layered, high-strength steel plates, reinforced concrete cores, and energy-absorbing composite materials that dissipate blast overpressure. Standard commercial blast doors are often rated for 50 to 100 pounds per square inch of reflected overpressure, while high-end private bunkers frequently specify 200 to 500 pounds per square inch or higher, equivalent to withstanding a near miss from a substantial conventional or low-yield nuclear detonation at a safe standoff distance. The doors incorporate multi-point locking systems with hydraulic or electromechanical actuators, capable of sealing within seconds during an alert. And they include manual backup mechanisms that can be operated by a small team even if primary power is lost.
Hermetic sealing is achieved through specialized elastomeric gaskets and inflatable seals that maintain integrity against both blast forces and chemical or biological agents.
Many installations use a series of 2 or 3 doors in an airlock configuration, creating a buffer zone where decontamination can occur before entry into the main facility. In advanced designs, the doors are also hardened against electromagnetic pulse effects, with conductive gaskets and internal shielding to protect sensitive electronics inside the bunker. Operation is deliberately slow and deliberate, often taking 30 to 90 seconds to fully open or close, to prevent rapid unauthorized access and to allow the structure to equalize pressure safely. These specifications are not arbitrary. They are derived from classified threat assessments and engineering standards developed by defense contractors and specialized bunker builders who also serve government clients. The result is an entry system that can survive direct or near-direct blast effects that would destroy conventional buildings
while still allowing controlled access for authorized personnel under emergency conditions.
Electromagnetic pulse protection represents one of the most technically demanding aspects of high-end bunker design. A high-altitude electromagnetic pulse event can induce damaging voltages and currents in any conductive path, including power lines, data cables, and even structural metal. To counter this threat, the facility is treated as a large-scale Faraday cage. The entire building envelope uses continuous conductive materials such as steel reinforcement, copper mesh layers, or specialized conductive coatings that create a closed electromagnetic shield. All seams, joints, and penetrations are meticulously sealed with conductive gaskets or welding to maintain shield integrity across the full frequency spectrum of an EMP event. Penetrations for air, water, and power are routed through waveguide below cutoff filters. These are metal tubes or honeycomb structures sized so that electromagnetic waves above a certain frequency cannot propagate through them. Power and data lines entering the facility pass through multi-stage surge protection devices, including metal oxide varistors, gas discharge tubes, and fast-acting semiconductor clamps designed to divert the rapid E1 component of an EMP. In critical installations, all external wiring is replaced with fiber optic cable wherever possible. Because optical fiber carries no electrical current and is inherently immune to electromagnetic induction, sensitive electronic systems inside the bunker are housed in additional nested shielded enclosures, often meeting military standards such as MIL-STD-188-125 or IEC 61000-4-36. These inner rooms use mu metal or high permeability alloys for low-frequency magnetic field attenuation. In addition to the overall Faraday cage, grounding and bonding systems are engineered with low impedance paths to safely dissipate induced currents without creating dangerous potential differences between equipment. Redundant power systems include isolation transformers and uninterruptible power supplies with EMP-hardened components, so that even if the external grid is compromised, the internal environment remains functional. Testing of these systems typically involves both computational modeling and full-scale pulse injection tests to verify performance against the three phases of an EMP event: the fast E1 pulse, the intermediate E2 pulse, and the slower E3 pulse that mimics a geomagnetic storm. The combination of enclosure shielding, waveguide penetrations, surge protection, and fiber optic isolation creates multiple independent layers of defense, making it extremely difficult for an electromagnetic pulse to disrupt critical life support. Security or communication systems inside the bunker. This level of EMP hardening is rarely discussed publicly, yet it forms a core part of the engineering specification for facilities intended to remain operational after a high-altitude nuclear event or severe solar storm. Around the facility, security layers include continuous artificial intelligence monitoring, thermal imaging, motion detection arrays, autonomous aerial patrols, and dedicated armed response teams maintained on permanent retainer, so activation time remains minimal. Ownership is deliberately separated from the individual. Assets are held through multiple corporate entities and trust structures situated in jurisdictions offering robust privacy and asset protection statutes. This architecture renders identification of beneficial owners and subsequent legal action prohibitively complex and costly. The bunker, therefore, functions as a hardened sovereign position, defended through both technological and jurisdictional mechanisms. A frequently overlooked dimension involves the persistent operational expenditure required to maintain readiness. Even during periods of non-occupancy, these facilities generate substantial annual costs. Security personnel remain on standby. Environmental, power, and structural systems undergo scheduled testing and maintenance. Consumable inventories are rotated to preserve viability. Technical and medical staff participate in recurring training and simulation exercises. The cumulative expense can reach several $1 million yearly, solely to preserve immediate activation capability. The 1% absorbs these carrying costs because the bunker represents terminal insurance. When all preceding layers of protection have been exhausted or compromised, this final option remains available and functional. High operational overhead does not preclude sophisticated financial structuring. Ownership is almost invariably routed through corporate vehicles and trust arrangements optimized for privacy, estate planning, and in certain jurisdictions, tax treatment. Maintenance and security expenditures can sometimes be positioned within legitimate business or estate frameworks, creating partial offsets. This approach mirrors the aircraft registration strategies examined previously, transforming what appears as pure consumption into a structured component of broader asset defense architecture. The bunker thereby becomes another sovereign-grade wealth container, difficult to locate, resistant to seizure, and embedded within protective legal engineering. When you put all the layers together, the pattern becomes clear. Rapid mobility platforms handle fast exit from unstable jurisdictions. Fixed underground installations provide long-duration autonomy and physical hardening. Both are supported by technological systems and legal structures that most people will never have the resources to replicate. Individuals at this level extend limited trust to conventional banking systems, governmental institutions, or assumptions of systemic stability. They instead allocate significant capital annually to preserve real optionality. The capacity to maintain control when external conditions deteriorate constitutes the fundamental differentiator between conventional wealth and wealth engineered for resilience across multiple threat scenarios. If you suddenly had access to substantial resources tomorrow, what would you choose to secure first? Would you direct those resources toward visible surface assets that remain easy for others to identify and reach? Or would you build systems that give you genuine alternatives when normal conditions no longer apply? Write your honest answer in the comments. I read every submission. If this examination has shifted your understanding of how substantial wealth is actually safeguarded, engage with the video and subscribe for continued analysis. Because the subsequent installment explores how remote territories are reconfigured into effectively autonomous jurisdictions operating with limited external oversight.